In section 7.2, we're going to see the rest of the exponent properties, so we're calling this exponent properties day 2. The first property that we're going to look at is the quotient of powers property. Remember, quotient means to divide, so it says let A be a non-zero real number, and let m and n be positive integers such that m is greater than n. So whenever I take two powers and divide them with the same base, all you're going to do is subtract the exponents. Just like when we were multiplying numbers with the same base, we added the exponents. So when we're dividing, we're going to subtract them. So if I had a to the m over a to the n, I would just simply take a to the m minus n power. So for example, 4 to the 7th over 4 to the 2nd would equal 4 to the 7 minus 2, which would be 4 to the 5th. So again, it's just the opposite that we did when multiplying, where we added exponents. Now that we're dividing, we're going to subtract them. So let's look at example number 1. Use the quotient of powers property. Part A, 9 to the 12th divided by 9 to the 5th. So even though it looks like a fraction, remember that just means to divide. So since I'm dividing, I'm going to subtract powers. So I would keep the same base, which is 9. I don't take 9 divided by 9 to get 1. I keep the same base, and I would just take 12 minus 5, which is 7. So I'm just going to leave it as 9 to the 7th. So part B, we have negative 2 to the 4th divided by negative 2 to the 3rd. Here we go with the parentheses again. Don't be confused by the parentheses. All they're saying is we want to take the negative and the 2 to the 4th power and the negative and the 2 to the 3rd power. So keep the same base, and let's keep it in parentheses. And we'll just subtract powers. So 4 minus 3 is 1. Anything to the first power is just that number. So to simplify completely, we could just say that that quotient is equal to negative 2. Part C, 6 to the 3rd times 6 to the 4th, all divided by 6 to the 2nd. When we do problems like this and you have multiple operations in them, act as if there are parentheses around the numerator and the denominator. And when you have parentheses, you do what's inside of them first. So we are going to take 6 to the 3rd times 6 to the 4th first. Since I have the same base and I'm multiplying, I'll add the exponent. So 3 plus 4 is 7. So now I have 6 to the 7th over 6 squared, or 6 to the 2nd. So now that I'm dividing, I'm going to subtract powers. So again, keep the same base, and 7 minus 2 is 5. So our final answer would be 6 to the 5th. In part D, I have 1 divided by r to the 5th times r to the 8th. So technically I have a division problem here because r to the 8th would be technically over 1. So then I'm just multiplying two fractions. When I multiply two fractions, I just multiply what's on top and divide by whatever's on the bottom. So 1 times r to the 8th is r to the 8th. And r to the 5th times 1 is r to the 5th. So now I just have a division problem, so I'll subtract the powers. So I keep the same base, and r to the 8th divided by r to the 5th. 8 minus 5 is 3, so my final answer would just be r to the 3rd. And now we have our next property, the power of a quotient property. So it says let a and b be real numbers with b not equal to 0. Because if b were equal to 0, I'd be dividing by 0, which is not possible. And let m be a positive integer. So in words, to find a power of a quotient, find the power of the numerator and the power of the denominator and divide. So if I have a over b all raised to the m power, that's just a to the m over b to the m. So for example, 3 over 2 all raised to the 7th, I just take the 3 and take it to the 7th power and the 2 to the 7th power to get 3 to the 7th over 2 to the 7th. So here is example number 2. Use the power of a quotient property. So part A says c divided by d raised to the 6th power. So all I'm going to do is take c to the 6th power divided by d to the 6th power. As long as I can't reduce anything else in here, I know I'm done. For part B, I have negative 2 divided by y all raised to the 4th power. Thinking back to the last section, we talked about what happens to negatives when raised to even and odd powers. With an even power, the negative goes away. With an odd power, the negative stays. So once again, I feel like it'd be useful for you to write down that a negative raised to an even power becomes positive, and a negative raised to an odd power stays negative. So let's go back to our problem at hand. It says negative 2 divided by y raised to the 4th power. So I have a negative raised to an even power. So our answer would be positive. So now all I have left to do is take each number and raise it to the fourth power, knowing that our negative sign is going to go away and our answer will be positive. So I'm going to take 2 to the fourth and y to the fourth. The only thing left to do would be to just multiply out what 2 to the fourth is. 2 times 2 is 4, times 2 again is 8, times 2 again is 16. So my final answer would be 16 over y to the fourth. There's nothing else that I could reduce. There's nothing up here that could reduce with anything down there, so that would be my final answer. And now let's look at example number 3. Use the power of a product property. So here's part A. We have 3a to the fourth divided by 5b, all raised to the third power. So the first thing I want to do, just thinking about the order of operations, is I want to make sure that there's nothing in our original fraction that can be reduced. The 3 and the 5 don't have anything in common. I have a to the fourth and b, so they do not have the same base values, so there's nothing I could do to simplify inside the parentheses. So next, I'm just going to take everything to the third power. Remember, the 3 is technically to the first power, and the 5 is technically to the first power. So when I have a power to a power, I multiply the power. So it would be 3 to the third, a to the 12th, since 4 times 3 is 12, over 5 to the third, b to the third. So the last thing I want to do is just multiply everything out. 3 to the third is 3 times 3 is 9, times 3 again is 27, and the a to the 12th would stay as it is, divided by 5 times 5 is 25, times 5 again is 125, and I have b to the third. I know that this is completely reduced and simplified, since originally I checked to see if there was anything in the inside of our original fraction could be reduced. So therefore our answer is completely reduced as far as we can. And now on to part B. X to the third divided by y, all raised to the seventh power, times 1 over 3x to the eighth. So we just need to make sure we follow the order of operations. So we first look inside of the parentheses and see if there's anything that can be reduced. Since it's an x on top and a y on the bottom, there's nothing in common, so it stays as it is. Next step in the order of operations is exponent. So I need to take everything in our parentheses to the seventh power. A power to power I multiply. So our first step is x to the 21st, since 3 times 7 is 21. And since there's technically a 1 on that y, it just becomes y to the 7th. The next step in the order of operations is to multiply and divide. So what I'm going to do is multiply straight across. So x to the 21st times 1 is x to the 21st, all over, and now I have y to the 7th and 3 times x to the 8th. So I just want to put everything in order, like alphabetical order. So I usually put the coefficient first, so that 3 is going to go out in front, and then x comes before y in the alphabet, so I'm just going to write that as 3x to the 8th, y to the 7th. My last step is to see if there's anything that will simplify. Since it's x's on top and I have an x on the bottom, I need to reduce those. Since this is division now, since x to the 21st is on top and x to the 8th is on the bottom, I'm going to subtract the powers. And wherever the bigger power was is where that answer will go. So I'm going to take x to the 21st divided by x to the 8th, which really just makes me take 21 minus 8. And 21 minus 8 is 13, and since the 21 was on top, the x to the 13th will stay on the top. Our x to the 8th is now gone because it canceled with 8 of the x's up here, so I just have 3y to the 7th left as my final answer. Next, let's look at a story problem. It says, example number 4. Below is a fractal tree that begins with a V-shaped segment, with each side of the V shape 1 unit long. Then add a V-shaped segment on each end with each side 1/2 unit long. So if you look at the first step, here's step 0, meaning the step before the first step. We start off with a V shape. This is 1 unit long, 1 unit long. Our first step then would be to start with that original V shape and then add to it V shapes on the end of them that are half as long as the original, just like it said. So sets of successively shorter branches are added so that each new set of branches is half the length of the previous set. So if you see here, we have that original V shape and then the 2 new V shapes that were half as long, and then on those stemmed off more V shapes that were half as long as the previous ones. So in part A, it says, make a table showing the number of new branches at each step for steps 1 through 3. Write the number of new branches as a power of 2. So once again, they only want us to write them for new branches for steps 1 through 3. So we're looking at step 1 first. We started off with this V shape, so we're not going to count these as the new branches. The new branches were these on top, and there were 4 of them. So remember, we're supposed to write these as powers of 2. So that means our base number is 2. So how can we write 4 as a power of 2? Well, just think about it. 2 raised to the second power is 4. Let's look at step 2. Remember, we're only counting new branches. So that's 1, 2, 3, 4, 5, 6, 7, 8. And remember, we're supposed to raise that to a power of 2. So 2 to the third is 8. Since 2 times 2 is 4, times 2 again is 8. And then finally for step 3, we have only the new branches. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 new branches, and we're supposed to write that as a power of 2. So you guessed it, since it was 2 squared, 2 to the third, 2 to the fourth, since 2 times 2 is 4, times 2 again is 8, times 2 again is 16. So if part B says how many times as great is the number of new branches at step 6 as the number of new branches at step 2. So first, let's think about how many new branches there would be at step 6 by examining the table. At step 1, we raised 2 to the second power. At step 2, we raised 2 to the third power. And at step 3, it was 2 to the fourth power. So notice it was always a power of 2, but with every step, it was always one more than whatever step you're on. So it was step 1, so we raised it to the second power. Step 2, we raised it to the third power. Step 3, we raised it to the fourth power. So in step 6, we would raise 2 to the seventh power. So back to the question, it says, how many times as great is the number of new branches at step 6 as the number of new branches at step 2? So just think about what this means, many times as great. If I ask you how many times as great is 10 as 2, that really just means 10 divided by 2 is 5. So you would say it's 5 times greater. So whenever you read something like this, it means to divide. So what we're going to do is take 2 to the 7th, divided by whatever it was at step 2. Well, at step 2, it was 2 to the third. So again, it ends up just being 2 to the 7th divided by 2 to the third. So remember, when you divide, you subtract the powers. So 2 to the 7th divided by 2 to the third is 2 to the 4th. So that means 2 to the 4th is 16. So it is 16 times greater at step 6 as it is step 2. So just to reiterate, whenever it's phrased like this, how many times as great is the number of blah, 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 that just means to divide. The bigger number divided by the smaller number. And here's example number 5, which I just realized has a typo in it, so I apologize, but we'll move past it. It says the order of magnitude of the luminosity of the Milky Way galaxy is 10 to the 36th watts. The order of magnitude of the luminosity of a gamma ray burster is 10 to the 45th watts. How many times as luminous is a gamma ray burster as the Milky Way galaxy? So once again, we have that phrase, how many times as whatever. So whenever it's phrased like that, that means we're going to divide. So we're going to take the bigger number, which in this case is 10 to the 45th because it was the bigger number, divided by the smaller number, 10 to the 36th. Remember, all you got to do is subtract the powers. So 45 minus 36 is 9. So it'd be 10 to the 9th as bright. That would be a 1 with 9 zeros. So that would end up being 1 billion. So really what that means is a gamma ray burster is 1 billion times brighter than the Milky Way galaxy. That's it for this section. Make sure you jot down anything you don't understand that we can cover in class before we move on, and we'll see you then.